Good afternoon, everybody. Thank you for joining me. My name is Paul Hillman from Eddyfi Technologies, and today I'm going to present a comparison of TFM inspection techniques with FMC and PWI firing sequences for stainless steel and dissimilar metal weld inspection. If you're watching live, feel free to ask some questions along in the chat. If you're watching this afterwards, then you'll see some contact details along with this presentation to get in touch with us. So in the presentation today, we'll start with a short introduction on recent progress in phased array UT technology. We'll then review the basic principles of FMC and PWI firing modes and some advanced imaging techniques like TFM. After that, I'll briefly talk about our newest phased array unit that allows to deploy this new technology. And the largest part of the presentation will be about the results of some case studies that we conducted to validate the benefits of the new tools for FMC, PWI, and advanced imaging techniques on the stainless steel and dissimilar metal weld samples. And finally, we'll present some conclusions. And thanks goes to my colleague Guy Mass for the material in this presentation and the results of the sample testing you'll see a bit later on. So it's fair to say that phased array UT is a mature and widely adopted technology, allowing for efficient inspections of critical components in various industries. And over the last 5 years, new techniques like FMC, its full matrix capture, and live TFM, being total focusing method, have been available on higher end phased array UT instruments. They've been introduced in recent codes as well, including the ASME code, section 5, and the ISO standards as well, 2 documents there. And dedicated training courses are being prescribed by the codes and are now being offered by some of the large training schools for dedicated 80-hour courses in TFM. But innovation is still happening, and NDT equipment vendors like us are constantly working on making the inspections easier to set up, increase the inspection speed, and improve the imaging quality. And in the presentation today, we'll see some results of the development efforts from the last 2 years. So to briefly review some principles, the full matrix capture method is a firing technique that consists in capturing and recording A-scan signals from every transmitter-receiver pair in an array. So each element of the probe is fired in sequence, and for each element that we fire, every receiving element collects an individual A-scan, and we store those in a matrix called full matrix capture. So at the end of a sequence for a probe with 64 elements, we have recorded a matrix of 64 squared, which is 4,096 A-scans per probe position. Then with this raw data, it's possible to take that and process it with an algorithm like TFM, either live or through post-processing to achieve optimal imaging. A more recent method that's being deployed now on portable equipment is plane wave imaging. It's an alternative firing technique that uses multi-element apertures in emission for pulsing instead of firing each element individually. So we might fire one or more discrete apertures depending upon the application. A bit like phased array and emission, we select a focal point and a desired sweep of angles. But in reception, we're saving individual elementary A-scans. So it typically consists of multiple focal laws with varying angles and apertures. And exactly like with FMC, we can use the data we record for PWI, for TFM imaging, either live or done through post-processing. And PWI data acquisition has several benefits compared to FMC data recording. The emitted pulse from the full aperture has more energy. We're not just firing individual elements, we're firing a large aperture. So we are enabled to get more energy into the region of interest, and it's more directional. We can pick, just like phased array beam steering, we pick which angle we want to and what position we want that energy. It provides greater sensitivity and then better SNR for a lot of applications, together with a much higher PRF and scanning speed because of significantly shorter firing sequences and less elementary signals to process. If in emission we choose, for example, 10 beams with our plane wave imaging algorithm, then we're storing 10 times 64 is 648 scans for a single probe position rather than 4096. And then we have less shots to wait for before moving on. So what do we do with that data, whether we get it from FMC or from plane wave imaging? We use TFM algorithm to calculate the resulting totally focused image in the area of interest. And the most commonly one, it's the most common algorithm that we use. And the most common one and done in live TFM is delay and sum, and the algorithm here sums the elementary A-scan signals from all the elements in the array to generate a frame of pixels, where each pixel is computed using a dedicated focused focal law. The TFM frames can be used for live interpretation, or you can store them for each position of the probe, and it's very similar in view to a dynamic merge view in regular phased array. The process results in nearly ideal focusing in each point of the near field zone of the active aperture within physical limits that we can achieve. And this improved imaging can allow for better characterization and sizing of challenging flaws. So the area is divided up into a grid of pixels, and each pixel is computed based upon the results of amplitude at the time of flight in the mode we select for every elemental pair. Something else that's recently introduced for live TFM is the envelope feature, and the TFM envelope is obtained from the magnitude of the summed analytical signals through a Hilbert transform. So it's a way of processing the A-scan to give us a magnitude of both the real and imaginary part of the A-scan. And the resulting live TFM image looks like a phased array signals with a smoothing filter applied. So it gives us a very nice image with nice smooth indications, but there are other big benefits to it as well. The main one being that the envelope delivers the same amplitude fidelity as the regular TFM construction while using a larger pixel size. So we can achieve the same amplitude fidelity, which is a code compliant value we need to achieve. And it's based upon the spacing of pixels in relation to the wavelength of sound that we're using, so that we ensure we're not more than 2 dB away from the real maximum amplitude if our probe is slightly misaligned based on pixels. And so with the envelope, we're able to achieve the same amplitude fidelity with a much larger pixel size. And with a larger pixel size, we can compute less pixels, or we can go faster. And typically, the use of the envelope will allow a reduction of the frame size by a factor of 4. And of course, the benefit as well is improved image quality. On the instrument side, the Emerald is Eddyfi's newest compact phased array UT system, and it includes all the advanced tools just mentioned, and it allows for high-speed data transfer as well, up to 150 megabytes per second for FMC elementary A scans, phased array UT data, and live TFM data. So with this instrument, you can choose to do live TFM, or you can store raw FMC data or PWI data. And you can do it at the same time as doing phased array channels, at the same time as doing TOF channels, etc. So a big benefit of this is carrying out code-compliant inspections with phased array whilst accompanying it with an advanced focusing technique as well. It's a 64-128 PR instrument with 2 separate conventional UT channels, and it's extremely well suited for performing TOF. It's in a rugged casing, IP65. It doesn't have any air intakes. There are some fans you can see on the end, just cooling the fins on the outside. And the Emerald is powered by Ultravision Classic, and that's the full package of Ultravision. So it offers the operator all the benefits from the complete design of inspection through to acquisition to analysis, from simple to very complex inspections, including FMC and TFM tools and reconstruction. So let's move on to some case studies. We'll start with a simple configuration in carbon steel. This is going to illustrate how the TFM envelope allows us to speed up the inspection of a 60mm thick component while maintaining image quality. And for this purpose, we're using the ASTM E2491 block. Lots of people use this for demonstrating TFM. It's got a set of vertical side drilled holes about 1 millimeter in diameter, very close together. So it's good for giving us spatial resolution indications. I'm going to use a standard 5 megahertz probe on here with 64 elements coupled to an L wave wedge, so 55-degree L wave wedge. And when we use a 256 by 256 frame computed in LL mode, the amplitude fidelity criteria of 2 dB is just satisfied. You can see that at the bottom left, it's an amplitude fidelity of 1.8 dB. And it allows for a maximum acquisition rate just above 50 hertz. And when we zoom in on the reflectors, the image quality is not really that optimal, but the code is being complied to. When we up the resolution to improve that image quality to 512 by 512 frame, the amplitude fidelity improves significantly to 0.4 dB, and also the imaging clearly improves. And we can see the facets of the wave making up those reflectors there as well. Unfortunately, when we do this, the maximum acquisition rate is reduced by a factor of 2 as well, to 26 hertz in this particular case. Now, when we use the envelope, this is with the envelope function enabled, we can see that even with a 256 by 256 frame here, we maintain the amplitude fidelity, the lower value of 0.4 dB, and we get the faster acquisition rate, therefore 53 hertz. So with the smaller frame size, we get the higher amplitude fidelity and keep the faster scanning speed. And we get nice, pretty smooth signals. So let's stay with the same probe configuration and specimen and compare the use of plane wave imaging firing sequence versus a complete FMC firing sequence. And plane wave imaging, here you can see the beams in emission displayed as the blue lines. And in this case, we've selected 7 laws. So we have a beam using the whole aperture at 20 degrees, one at 30, one at 40, all the way to 80. So comprising 7 beams in total. And again, we're storing all the elemental A scans. And the red area there is the area we're going to compute the TFM image. And on this slide, we can see the images from a 256 by 256 TFM LL reconstruction, so direct path reconstruction, on another set of side drill holes on that same block. It's the radius holes there. So the image on the left is the plane wave imaging with TFM, and the image on the right is the FMC with TFM, both with the envelope as well. The amplitude fidelity is the same. We get 0.4 dB amplitude fidelity in these setups, but you can see that the acquisition rate is much higher with the PWI one. So we're more than 3 times higher with the acquisition speed. And if we were collecting at 1 millimeter increment, that would be 179 millimeters per second in that case. And when we zoom in on the 2 1 millimeter holes, you can see these are only slightly spaced apart at 1.1 millimeter. We can see they're both clearly resolved in the PWI firing sequence and the FMC firing sequence with very similar results. Let's now get into austenitic materials and see how the advanced focusing techniques perform in more challenging inspection configurations. First, we'll compare various imaging techniques on 304 stainless steel base material. This base material is relatively fine grained structure, so we tried to use the same 5 megahertz pulse echo probe, an L wave wedge, the 55 L wave wedge, from the first case study in carbon steel. The considered specimen is 2 inches thick and contains a number of simulated branch cracks, which were made using wire EDM. As you can see on the image, the morphology of the simulated cracks is very complex with many facets. On this next slide, we have the 2 floors in the same image, the 0.55 and the 0.25 inch high, located at the far surface. The image on the right is from the live FMC TFM with envelope. The images of both floors seem very accurate and the resolution is very good. The height sizing at 0.25 inches is exact. On the left side, we have the PWI TFM image. In this case, we generated it with 15 plane wave pulses in the firing sequence. And actually, the image is very similar to the FMC TFM image as well for SNR. The quality of the imaging and its benefit for floor characterization is even better demonstrated when we overlay the actual floors on the recorded data. The multiple facets of the complex floors you can see are clearly resolved, and the relatively high frequency and the large aperture of the probe allow us to fully exploit the potential of the advanced focusing techniques. When we compare the maximum acquisition rate that can be obtained, the benefit of the PWI firing sequence is obvious. In this case, it's 2 times faster than the FMC firing sequence, and even 20% faster than if we did standard phased array UT on this type of setup. All the images that have shown up to now involve live TFM processing of the FMC or PWI raw data while the inspection is ongoing. But in some cases, specifically for challenging floors and damage mechanisms, it can be useful to record the raw data for offline processing. And in UltraVision Classic allows us to reconstruct various types of data groups from the raw data, including standard phased array and TFM. And there's a number of different TFM algorithms that can be used as well. So the standard delay and sum algorithm is there to recompute new TFM images from the raw data. But we have some additional ones as well. We have a delay multiply and sum. This one sums the delayed pulsar receiver A scans multiplied by each other. And it reduces the well-known TFM artifacts. When you see a TFM image, particularly in the presence of large reflectors like back wall, you will tend to see a elliptical or circular type artifacts, which is common in the delay and sum algorithm. Using this one, we reduce that whilst maintaining the indications from the floors and increasing, in a lot of cases, the SNR. And we also have TFM with phase coherence factor. And this is taking a weighting of the phase-related information from a particular pixel or indication and weighting that along with the amplitude. So not completely amplitude independent in this case, but gives us a good contrast of tip information of where we're very well in phase, and also from planar reflectors as well, maintaining signals from these. Skipping ahead a little there. And the TFM envelope, of course, is there from the Hilbert transform, and it can be applied with either of those 3 TFM algorithms simultaneously. And the next slide shows images of the same floors, but this time we were reconstructed from the recorded raw data. We have the PWI firing on the left and the FMC firing sequence on the right. And this time, instead of the delay and sum, we use the delay multiply and sum algorithm with envelope for both of those reconstructions. And you can clearly see a vast improvement in the global signal to noise ratio on both images. Just for comparison, we can flick back to the original there, doing the live delay and sum to compare it to the reconstructed delay multiply and sum. It's very clear to see the reduction in background noise. Okay, using the same specimen, we're going to turn it over in this next example and have the probe on the same surface as where the cracks are originating from to look at performance and characterization of sizing of near surface cracks in the austenitic based material. And this time we're going to look at that 0.85 inch deep crack. Again, we have PWI on the left and FMC TFM on the right. The quality is very similar across both of those type of reconstructions. And the speed, again, is by about a factor of 2. And we're picking up the facets of that crack very nicely. And if we overlay the image there, you can see facets of that crack being detected. It's worth noting that this is one reconstruction mode, the direct path LL. Of course, we can use multiple reconstruction modes at the same time to be sensitive to other areas of that floor. The next case study is about inspection of dissimilar metal or DM welds. These welds are typically join two or more different materials and mostly involve Inconel alloys. They are often used to connect cladded carbon steel vessels to stainless steel piping, and they're very challenging for UT inspection due to the various propagation issues in austenitic structures and the presence of multiple acoustic interfaces. And sometimes they have very complex geometry, including nozzles and tapers as well. And effective inspection techniques for DM welds are typically based on low frequency probes, a 1.5 megahertz dual 2D matrix array or DMA probes. This is where we have two matrix probes separated by an acoustic barrier. And it offers better sensitivity in SNR due to the convolution of transmitter receiver beams, avoiding ghost echoes as well from internal wedge reflections. And in this case study, we're going to have a look at inspecting a dissimilar metal weld specimen with a wall thickness of 1.2 inches, containing a large branch crack on the ID surface. We're using an optimized large aperture dual matrix array probe here. Both transmitter and receiver sides have 10 by 6 elements, so it's 60 elements in a grid of 10 by 6 for the transmit, and the same on the receive side. As a reference, the image on this slide here on the left is the beam simulation from a standard phase array UT setup focused at the ID surface. So let's have a look at the differences from the two techniques, or the different techniques. The merged view is the best practice for phase array UT inspection representation, where we're looking at a volume of data and are able to slice through that. The corner trap is very well detected because the lower angles of the sector scan are typically focused near the ID. The top view, by the way, is the phased array, standard phased array focused near the ID, and the bottom view is the live FMC TFM of that region displayed on the right-hand side. And you can see the morphology, intended morphology of the crack in the diagram to the right. So the image with the live TFM also sees the corner very nicely, but also has a good detection of the tip. You can see very well in the B scan there, and also in the end scan on the right hand side. Whereas the phased array has great detection of the corner because we're focused at the corner on the ID, but we're missing most of the tip of that crack, both because we don't have beam steering up that high, but also we're not focused in that region. The next slide, replacing the top one there, is the reconstructed TFM delay, multiply, and sum and envelope in LL mode. So both images, you clearly see the corner and the tip. Certainly the SNR has a significant improvement using the DMAS reconstruction, and we're removing all of those elliptical artifacts seen on the end scan of the live FMC TFM as well. Of course, it's also possible and prudent in most cases to construct the TFM image with alternative wave paths. Can be done in both live TFM and reconstructed from FMC or PWI data, where you're able to select whichever wave path you wish to compute your new TFM image with. And from the branch crack, the 3L mode, LL-L, clearly confirms the ID connection and some through wall extent of the floor with a high signal to noise ratio, allowing for reliable length sizing. On the other hand, the higher parts of the floor are not really visible with the 3L mode. So it shows us that multiple techniques are often required for full detection and characterization. The last case study we'll look at today involves cast austenitic stainless steel, cast welds, Such welds are typically located in safety significant locations in reactor coolant system of pressurized water nuclear reactors. The ultrasonic examination of cast components and welds is very challenging because of the anisotropic and coarse grain structure of the material. Individual grain sizes can be very large, maybe more than 10 millimeters. The grain structure shown on the right of this slide is representative of the specimen that we used, with an equiax grain structure on one side, a columnar grain structure on the other side with a weld filler material. In this case, we have a crack, a thermal fatigue crack in the weld bevel. It's got a length of about 2.4 inches and a height of about 1 inch. Best practice inspection techniques for CAS use dual matrix array probes at low frequencies between around 0.5 megahertz to 1.5 megahertz to reduce the attenuation in the coarse grain austenitic structure. In this case, we used a large aperture DMA probe of 1 megahertz with 10 by 5 element configuration for both the transmitter and receiver. And you can see a picture of that in the bottom right on that block. So again, we're going to compare some different techniques, and this one compares the live PWI TFM data on the top with the live FMC TFM data below. Both the corner trap and the tip contour of the long crack are very well detected in both cases. The signal to noise is around 10 dB in both images, and that's a comfortable detection range for inspection of this type of difficult material. The TFM images, in combination with the large aperture of the DMA probe, provide fairly good resolution, even at this low frequency. The PWI TFM data on the top of the slide was generated with only 8 plane wave pulses in the firing sequence, resulting in maximum acquisition rate of 140 hertz, which is 4 times faster than can be done for the FMC TFM data. And here is that data again, now reconstructed in post-processing using the TFM delay multiply and sum algorithm. Again, plane wave imaging firing sequence on the top and FMC firing sequence on the bottom. In both cases, the DMAS algorithm provides an improvement of the signal to noise of more than 6 dB, so double compared to the live images, with a slight advance for the reconstruction of the raw FMC data. Overall, we can conclude that the advanced focusing techniques perform very well in combination with the low frequency DMA probes. In addition, recent optimizations in the raw data saving process have drastically increased the inspection speed, especially for PWI firing sequences with low frequency probes. To conclude, based on the results of the case studies that presented here, we can draw some conclusions. Advanced focusing techniques have become important assets in the phased array UT toolkit. They can improve the resolution of floor images and increase the inspection coverage with focused beams. Of course, active aperture and frame resolution are key parameters for the TFM technique and must be carefully selected to exploit the full potential of the technique. And the plane wave imaging firing sequence and the TFM envelope allow to drastically increase the inspection speed whilst maintaining image quality. Selection of appropriate probes in terms of frequency, wave mode, wedge angle remains a key requirement for success, especially for austenitic materials and welds, where the employment of these low frequency L-wave DMA probes is paramount. When FMC or PWI raw data have been collected, the use of different wave modes and advanced processing algorithms can improve the detection capability on challenging material and flaws. And now with the PWI raw data saving as well, we can go much quicker than previously could happen with FMC raw data saving, and becoming much more efficient for capturing live inspection data and raw PWI data for post-processing offline. And thanks for your attention. It's the end of the presentation. I don't know if we have some questions. A question here about how do we save the raw data for reconstruction later? There's a few ways to do it. With the Emerald, you're controlling it from Ultravision Classic. So in that setup in the sequence, you set up TFM acquisition, and then you have the option to select saving of raw FMC or PWI, and you get a companion file alongside your UV data file with the raw FMC data in it, which when opened together, you can do the reconstruction. It's also possible on Topaz 64 to save it locally on the instrument and transfer it over to Classic later on. Is there any update of the software as far as handling goes, file sizes and scan speed? Yeah, I mean, when you run this, when you run the Emerald from UltraVision Classic, your file size is potentially unlimited. You're limited by the capability of the computer you're using to run it, but you can have very large file sizes in the region of hundreds of gigabytes in some cases I've seen. With scan speed, it's important to optimize your firing sequence, and plane wave imaging really gives us a huge benefit for improving scan speed by offering the shorter firing sequence whilst maintaining the quality of TFM imaging. Which instruments support plane wave imaging? So on the Zetec brand side of Eddyfi, we have the Emerald, the latest one I showed. We have the Topaz 64 as well, supporting plane wave imaging. And on the M2M brand side of Eddyfi, we have the Gecko and the Panther, all supporting plane wave imaging. Another question here, does the technique TFM PWI give satisfactory results if we only scan on one side, such as pipe to fitting? I think this really depends on the type of flaws and angles you're trying to find. Certainly, making sure you're introducing sound at the right angles in the first place to find the flaws is critical. So it's not a magic silver bullet to solve every application. It could be investigated for some things, doing one-sided, but with caution, I would say. You still, I would say, apply first principles on inspection technique design for optimizing that. But for difficult applications, I guess it could give some benefits. How many live TFM frames can the Emerald support? So it can support 2 FMC acquisitions simultaneously and 4 reconstructions from each of those. So you could have 8 TFM frames simultaneously, live TFM frames simultaneously with the Emerald and Topaz 64. Okay, if you have any questions after this, please feel free to contact me or my colleagues. Thanks for your attention.